So, welcome to this lecture 5 of our course on fundamentals of transport processes. We were going through integral and differential calculus with vectors in order to set the stage for deriving conservation equations for the fluid velocity field, which itself is a vector. As I said, we are doing some preparatory courses in order to familiarize ourselves with how one can do calculus, integral and differential, considering vectors as objects in themselves rather than trying to do them for the individual components. So, our starting point, vector calculus in just one dimension. I defined for you what is meant by the derivative of a function and what is meant by the integral. So, if I have a single valued function y of x, single valued means that at each value of x there is a unique value of y. If I want to define the derivative at a point, I take a small interval delta x around this point x and find out what is the variation in y when I have traveled this small interval delta x, that is delta y. In the limit as delta x goes to 0, delta y will also go to 0, but the ratio need not. And the limit as delta x goes to 0, the ratio is what is called the derivative of the function at that particular location. So, limit as delta x goes to 0 of delta y by delta x is equal to dy by dx. Alternatively, delta x times the derivative, the interval times the derivative gives you the difference in the dependent function y. And the integral form of this is that integral between two endpoints of dx times the derivative is the difference in y between those two endpoints. So, we use this analogy to define our first derivative function, that is the gradient. Okay. Grad t, okay, this defined such that delta t, that is if I am sitting at one particular location x and I move a small distance delta x to a new location, the change in temperature, say between these two, the final minus the initial point, is equal to this gradient of t dotted with the displacement, okay, gradient of t dotted with the vector displacement that was moved. So, the gradient of t tells you how the temperature is varying, is changing locally as you move some distance around this point. Okay. But even though the gradient I had defined in terms of the partial derivatives, grad t was equal to partial t by partial x 1 E 1 plus partial t by partial x 2 E 2 plus partial t by partial x 3 times E 3. So, even though grad t was defined in terms of these partial derivatives, the gradient vector itself has a direction and a magnitude that is independent of the coordinate system that I am using to analyze the problem. It is well defined because if I go from one location to the next location, the difference in temperature has to be grad t times delta x, regardless of what coordinate system I use to represent grad t and delta x. The result that I get has to be exactly the same, independent of coordinate system. So, grad t is a vector which is independent of the underlying coordinate system. It has a magnitude which is independent of underlying coordinate system. That means that the magnitude of grad t is equal to partial t by partial x 1 the whole square plus whole square to the half power. This is independent of coordinate systems used, and it has a direction also that is independent of coordinate systems used. Okay. I had given you a physical interpretation of grad t. Okay. If I sit at one particular location and I move a small distance, the distance is the same, the direction is different. So, I move a small distance of equal length in different directions and I look at the change in temperature. Change in temperature is grad t dotted with delta x. So, that change in temperature is going to be the largest where grad t and delta x are in the same direction. what that means is that grad t is in the direction of maximum variation of t, and if I move in a direction that is perpendicular to grad t itself is a vector at a given location. If I move in a direction that is perpendicular to grad t, then grad t dot delta x is equal to 0, because cos theta, the angle between them is 90, therefore, the cos theta is equal to 0. So, grad t dot delta x is equal to 0 if you move in a direction perpendicular to grad t. That means that the gradient of a scalar field is directed in the direction of maximum variation of that scalar field. It is perpendicular to surfaces of constant value of that field. So, in order to identify surfaces of constant temperature, I just need to locate the gradient of that temperature and then look perpendicular to that. Perpendicular to the gradient at every point is a surface of constant temperature. We had also derived the integral relation corresponding to grad t, and that is that if I take grad t integrated with a differential displacement and then integrate it from one initial to a final position, that is equal to the difference in temperature between that initial and final location. This we had seen by dividing this entire path between these initial and final positions into small differential intervals, and then summing up grad t dot delta x on each of these intervals. And obviously, the temperature at each point along that path will cancel out, because it has a positive sign on one side and negative sign on the other side. You are just left with the temperature difference between the initial and final locations. So, that gave us the integral relation for grad t. The integral between two locations A and B of the differential displacement dx dotted with grad t was equal to the difference in temperature between the initial and final locations. This has consequences or corollaries. If I take different paths between the same two endpoints, integral of dx dot grad t has to be the same on all of those paths. Okay. If I take different paths between the same two endpoints, this integral has to be exactly the same on all of those paths. Secondly, if I start from one location, come back to the exact same location, this integral has to be 0. dx dot grad t, the integral has to be 0 if you start from a given location and come back to the exact same location. Our next derivative was the divergence. Divergence acts on a vector in general, okay, and we had defined it as, if I want the divergence at a given location x vector, I go to that point x and I construct a small differential volume delta v around this point. I had expanded out this volume delta v for you. Delta v has a surface S. Each point along the surface, you can define the unit normal n, that is shown by the red in this figure. At each point, you define the outward unit normal directed outward from this volume. You take the dot product on the surface of the unit normal times the vector A itself. As I said, vector A is a single valued function at each point on that volume. So, you take the unit normal dotted with that vector A itself, integrate over the entire surface and divide by the volume, and that gives you the divergence. Since I have taken n dot A, the result that I get is a scalar. Okay. I have taken n dot A, integrate over the surface, divided by the volume. So, the divergence will also have dimensions of this vector divided by distance. Okay. And I will give you a physical interpretation of divergence in terms of the heat flux or the mass flux. Integral ds n dot q is the total amount of heat coming out of the surface per unit time. So, for this differential volume, the total amount of heat coming out of the surface per unit time is equal to the volume times the divergence of q. Okay. So, that in this case the divergence has dimensions of q divided by distance. We had calculated the divergence in a Cartesian coordinate system. Okay, limit as delta v goes to 0, integral ds n dot a divided by delta v. So, in this Cartesian coordinate system, we construct a differential volume with surfaces along perpendicular to lines of constant coordinate. Okay. So, you have two surfaces perpendicular to the x1 direction, the front and the back, two surfaces perpendicular to the x2 direction, right and left, two surfaces perpendicular to the x3 direction, up and top and bottom. And we have to take this ds n dot a on each of these surfaces. Okay. So, on the surface on the right, n is the outward unit normal, it is in the plus E2 direction, and since my volume is centered at x1, x2, x3, surface on the right is at x1, x2 plus delta x2 by 2 and x3. Okay. So, I take E2 dotted with a vector at the location x1, x2 plus delta x2 by 2, x3 multiplied by the surface area. In this case, the surface area is delta x1 times delta x3. Okay, so, that is on the right side. On the left side, the unit vector is in the minus E2 direction because it is outward to the surface. Okay, the unit vector is in the minus E2 direction because it is outward to the surface, dotted with a at x1, x2 minus delta x2 by 2 and x3 multiplied by the surface area once again. We do this for all surfaces, right, left, top, bottom and front and back. And so, I get a total of 6 terms here, okay, 3 of which are positive, 3 of which are negative, and then I have to divide by the area. And when I divide by the area, okay, I get a2 at x1, x2 plus delta x2 by 2, x3 minus a2 at x1, x2 minus delta x2 by 2, x3 divided by delta x2. Similarly, in the x1 direction and in the x3 direction. And finally, the final expression for the divergence turned out to be quite a simple one, partial a1 by partial x1 plus partial a2 by partial x2 plus partial a3 by partial x3 in the Cartesian coordinate system. So, let us write that out. Divergence of a vector is equal to I can also write this as E1 partial by partial x1 plus E2 partial by partial x2 plus E3 dotted with A1 E1 plus A2 dotted with A1 E1 plus A2 E2 plus A3 E3. Okay. So, this basically is equal to gradient dotted with this A vector. Okay. So, that is why the divergence is often written as del dot A. Okay. Note that this I had done quite simply because when I take the derivatives partial by partial x1 of a1 E1, okay, I have assumed here that partial by partial x1 of a1 E1 is equal to E1 times partial a1 by partial x1. That was the assumption when I expanded out the derivative. Okay. This is true for a Cartesian coordinate system. Okay. When I have a Cartesian coordinate system, this unit vector E1 does not change as I go from one location to the other. It is exactly the same at every location. The magnitude is the same, the direction is the same. Therefore, the derivative of E1 with respect to x1 is identically equal to 0. Seems quite a simple point, but as it turns out when we go to other coordinate systems, this is no longer true because the unit vectors actually do depend upon position, and that is something that we will be careful about when we extend this to other coordinate systems. Okay. So, that is the divergence. The definition of divergence is formula del dot A. Okay. And what is the integral relation for the divergence? Okay. So, this is the derivative. The equivalent integral relation is that for any volume V, okay, with a surface S, for any volume V with a surface S, integral over the surface of n dot A is equal to integral over the volume of divergence of A, where n is the outward unit normal to the surface. Seems very similar to the formula that I had for the definition of the divergence, except that this is not in the limit as delta V goes to 0. This is at for any volume which is a closed volume which is bounded by a closed surface. For any volume, integral over the surface of n dot A is equal to integral over the volume of divergence of A. Okay. So, this is the integral theorem, this is called the divergence theorem. Okay. Note that it relates the integral over the surface to an integral over a volume. Okay. That is, the integral over a volume integral is related to a surface integral. Okay. If you recall, the integral relation for the gradient was defined as integral dx dot grad t is equal to Tb minus Ta. So, this basically related the integral along a line to the difference in the endpoints. Okay. So, this for the gradient, the integral theorem related the integral along a line to the difference at the endpoints, whereas for the divergence, it relates a surface integral to a volume integral. Okay. So, let us try to explain how this comes about. Okay. So, let us first take integral over the volume. Okay. Of divergence of A. Okay. Integral over the volume, this volume V of the divergence of A. Okay. So, how do I calculate this integral over this volume? What I can do is to divide this volume into a large number of small differential volumes. Okay, and divide this into a small number of differential volumes. I call this is volume 1, 2, 3, etc. So, this is volume 1, this is volume 2, this is volume 3, volume 4. And I can write this as summation over all of these differential volumes. Okay, of divergence of A at the location x1 times delta V1 plus divergence of A at x2 times delta V2 plus etc. plus divergence of A at xi times delta Vi plus divergence of A at xi plus 1 times delta Vi plus 1 plus etc. Okay. So, I divide this into small differential volumes and I take the divergence of A at that location times the volume itself and I sum it over all of those volumes. So, let us take two typical volumes. I will just expand it out. Okay. This is volume I. The next one is the next differential volume. This is volume I plus 1. Okay. So, if I take divergence of A at xi times delta Vi, okay, for this I can now apply the divergence theorem, because this is now a differential volume. For this I can now apply the divergence theorem, because this is now a differential volume. So, for this differential volume, this divergence of A times delta V I over this differential volume can be written as integral over the surface of n dot A, okay, over the surface S I, okay, of n dot A. Okay. For the adjacent volume, divergence of A at x I plus 1 1 times delta V I plus 1 is equal to integral of the adjacent surface S I plus 1 ds n dot A, okay, where n is the outward unit normal, A is the vector at that particular location on that surface. Okay. So, let us look at these two adjacent volumes. Okay. So, for the volume I, right, on this surface they have one common surface, and that common surface is this one. Okay. This is the common surface between the two. Okay. For the volume I, the outward unit normal points in this direction, okay, it is outward to the surface, and at the integral of n dot A, outward unit normal dotted with A on this surface for the volume I. If I go to the next adjacent volume I plus 1, okay, if I go to the next adjacent volume I plus 1, at this common surface, the outward unit normal to the volume I plus 1 actually points in the opposite direction. Okay. Value of A is the same for both volumes I and I plus 1, because it is the same surface. For the surface, for the volume I, the outward unit normal is in the right direction. For the volume I plus 1, the outward unit normal is in the left direction. Okay. So, on this common surface, this integral ds n dot A, okay, for these two, it is equal in magnitude, because A is the same, unit normals are in opposite direction. That means that the value of this surface integral contribution to the divergence of A dot del V cancels out on this common surface, because it is between two volumes. The value of the function itself is the same on that volume, unit normals are in opposite direction, therefore, it cancels out. Okay. All surfaces integrals on surfaces which are in between two differential volumes will also cancel out for that same reason. Unit normals are opposite, the value of the function is the same. Okay. So, the only surface integrals that I will be left over are those that are not between two differential volumes, that is the surface, that is the outer surface to this entire volume. Okay. The outer surface to the entire volume is the only surface that will be left out. Okay. So, this becomes equal to integral over the outer surface of ds n dot A. Okay. So, integral over the outer surface of ds times n dot A. Okay. So, this is the divergence theorem, okay, for divergence, the integral relation for divergence, just as I had the differential relation for divergence earlier, the integral relation for divergence is this one. Okay. It relates the volume integral to a surface integral. Okay. Physically, if this, for example, was the heat flux or the mass flux, okay, if what I had here was the heat flux or the mass flux, okay, let us say the heat flux Q. Okay. This integral ds of n dot Q, okay, integral ds of n dot Q is the total heat coming out of this volume per unit time, because n dot Q is the component of the flux along the outward unit normal, and n dot Q is the amount of heat coming out per unit surface area per unit time. That means that integral ds n dot Q is the total heat coming out per unit area per unit time. That is equal to the volume integral of the divergence of Q throughout this entire volume. So, what this is saying is that this volume integral, okay, divergence of Q integrated over the entire volume, okay, this integral does not depend upon the values of this vector within the volume. You can find out the value of this integral just by knowing the values of this vector along the surface alone. Okay. So, that is the physical implication of this particular statement, that the value of this divergence of Q integrated over a volume does not depend upon the value of Q within that volume. it depends only upon the value of q on the surface. Okay, so, there is a physical implication of this particular statement. So, that is for the divergence. The definition of divergence in a Cartesian coordinate system, it is equal to gradient del dot A. Okay. It is equal to del dot A in all coordinate systems. Only thing is that divergence operator itself changes, and we will see that a little later. And the integral relation for the divergence, that is integral over the volume of dV times divergence of a vector, is equal to integral surface of n dot that vector. Okay. So, the third thing, the third differential quantity that we shall be dealing with is curl. Okay. Once again, we take a small volume V, I will call it as delta V. Okay, with a surface S and with unit normal. Okay. The curl of A is defined as integral over the surface of n cross A divided by delta V, limit delta V goes to 0. It is defined as integral over the surface of n cross A divided by delta V in the limit as delta V goes to 0. Obviously, I have taken the cross product of two vectors. So, curl ends up being a vector, okay, because I have taken the cross product of two vectors, curl ends up being a vector, and I have on top a surface integral of n cross A divided by the volume. So, once again it has dimensions of A divided by length. Okay. Now, once again, if I wanted to calculate the value of this curl in the Cartesian coordinate system, I could do the same integral over the surfaces that I had done for calculating the value of the divergence. Okay. However, it is not really necessary to do that, because I have already given you a way of expressing the cross product as two dot products. Okay. I have already given you a way of expressing the cross product between two vectors as a product of two dot products. Okay. So, if I were to write this in Cartesian coordinate system, we will get limit as delta V goes to 0, integral ds epsilon I j k n j a k by delta V. This antisymmetric tensor, of course, is a constant. Okay, it is independent of position. Okay, so, the antisymmetric tensor does not depend upon position. Therefore, I can write this as, okay, I can take it out of the take the antisymmetric tensor out, and I will get epsilon I j k limit as delta V goes to 0, integral ds n j a k by delta V. Okay. And of course, this thing I had already evaluated for you in the context of divergence. Okay. This I had already evaluated for you in the context of divergence, and you know that this is equal to epsilon I j k partial a k by partial x j. Okay. So, this is equal to epsilon I j k times n j a k. If I integrate over the surface, I will do the same calculation that I had done earlier. Okay. For this Cartesian coordinate system, n will have one index, a will have the other index, and I will take the difference on these 6 surfaces. Okay. The unit normal, the outward unit normal points in opposite directions on the two opposing phases, and because of that I will get the difference in a between those two opposing phases. Okay. And that will translate to a derivative, and so this is just equal to epsilon I j k times partial a k by partial x j. Okay. It can also be written as del cross A. Now, we are used to the cross product as in the matrix form, okay, E 1, E 2, E 3, d by dx 1, d by dx 2, d by dx 3 a1 a2 e3. That is del cross A, and you will get exactly the same result if you use this formula. Okay. Okay. So, that is the derivative form of the curl. Okay. Curl of a vector gives you another vector is equal to n cross A integral over the surface divided by delta V, and for a Cartesian coordinate system, if my surface if I take a cubic volume, this can just be written as epsilon I j k partial a k by partial x j or del cross A. Note that in this particular relationship, there is one unrepeated index, that is I, the other two are repeated, that means that there is only one unit vector, and therefore, the result that I get is a vector. Okay. So, this is nothing but the gradient of A dotted 2 times with this antisymmetric tensor. Okay. What is the integral relation? Okay. If you recall, for the gradient, the integral relation related the integral along a line to the difference between the endpoints. For the divergence, the integral relation related the integral over a surface to the integral over a volume. For the curl, the integral relation will relate the integral over a surface to the integral over a line. Okay. So, that is the integral relation for the curl. So, let us look at that. So, if I have some open surface, with some perimeter. Okay. So, this this is the perimeter C of the surface, and this thing use black for that. This thing is the surface S. So, this is an open surface S with a perimeter C, okay, with a unit normal n at various points along the surface. Okay. And what the integral theorem states is that integral over the surface of the unit normal dotted with the curl of a vector is equal to integral over this closed loop C, okay, of dx dotted with A. Okay. Integral of n dot curl A over, take C down, okay, integral of n dot curl A over this entire surface, okay, over this entire surface is equal to integral over the closed loop of dx dotted with A. Okay. So, that is the integral theorem for curl. How do we prove this? Okay. So, if you recall, the definition of the curl related a surface integral and a volume. The curl as defined was a surface integral divided by the volume. So, you cannot prove it straight away, you cannot straight away relate a line and a surface integral. What you need to do is to construct a small volume around the surface. Okay. So, let us take a little patch of surface here. Okay, let us take a little patch of surface. Okay. So, if I look side on from the surface, okay, I will see this as the surface, and I can also look from the top. Okay. So, this little patch of surface, if I look from the top, it will look something like this. That is the little patch of surface if I look from the top, and from the side, so this is side and this is top view. Okay. So, I construct a small little cubic volume around this surface. Okay. The volume actually straddles the surface, it is both above and below the surface. Okay. It has a certain height h, let me move the surface a little bit. So, this is the surface, okay, and this volume has a height h, okay, and there is a unit normal to this surface n. Okay. So, if I take the volume on at the bottom here, it will look something like this. Okay. There is the volume looking at from the top, and from the side view it will be both above and below the surface. Okay. So, I have a unit normal n to the surface itself. Okay. In my definition of curl, I have to take n cross A. Okay. In my definition of curl, I have to take n cross A for the differential volume. So, I have to define a unit normal to the differential volume also. Okay. So, in this case, I have to define a differential volume for an outward unit normal for this differential volume itself. That outward unit normal is directed in different directions at different surfaces. Okay. So, I will call that outward unit normal as capital N. Okay. Okay. So, it is right and left, front and back, and above and below is directed in different directions. This outward unit normal for the volume is capital N. So, for this little differential volume, if I take, note that small n is the unit normal to the surface. Okay. It is directed only in one direction. Okay. It is the outward unit normal to the surface. Capital N is the outward unit normal to the cubic volume that I have constructed around the surface. Okay. Capital N is the outward unit normal to the cubic volume that I have constructed around the surface. So, if I look from the top, I will have unit normals in all of these directions, as well as one coming out of the board, the other one going into the board. Okay. So, these are unit normals to the top and bottom surfaces. Okay. So, if I take this n dot curl A, okay, n dot curl A is equal to 1 over, okay, for this differential volume, 1 by delta V integral over all the surfaces. Okay. Let me call this differential volume surface as sigma, in order to not confuse it with the surface S that I already have. Sigma represents the surfaces of this cubic differential volume that I have constructed. Okay. Sigma of n dot curl A, of n dotted with curl A was capital N cross A. Okay. N dot curl A was capital N cross A. Okay. This n dot n cross A you are probably familiar with. It is what is called the triple product. Okay. So, n dot n cross A is equal to, I am taking the dot product of this times the curl epsilon I j k n j a k. Okay. And when I take the dot product, the indices are repeated. So, this just becomes equal to n I epsilon I j k n j a k. Okay. It is a good place to now introduce the triple product. Okay. So, this you are familiar with. This can be written as n 1, n 2, n 3, n 1, n 2, n 3, a 1, a 2, a 3. Okay. That is the matrix form. In indicial notation, we will just write it in this particular fashion. Okay. However, you know that n dot n cross A, right, you can interchange the order, okay, because you can, if you interchange two rows, okay, you will get back the same matrix. Okay. So, I can also write this as A dot n cross n. Okay. I can also write this as A dot n cross n, okay, because it is a triple product. Okay. And the same thing you will get out of here. So, this will be equal to A k epsilon k I j n I n j. Okay. When I go from epsilon I j k to epsilon k I j, I have interchanged indices two times. First I interchanged I and j, then I interchanged j and k. Okay. So, because of that I get back the same result. So, the triple product, okay, if you go in a cyclical fashion, it remains unchanged. Okay. Good. So, this is the triple product, and as I said, I can write this as A dot n cross n. Okay. So, let us use all of this. Okay. So, this I can write it as 1 by delta V integral d sigma of A dot n cross n. So, what is this A dot n cross n? N is this vector, okay. It always points upward. Okay. N is this vector, it always points upward. Capital N is the vector that is perpendicular to the surface. On the top and bottom it is upward and downward. On the front and back it is pointing out and into the board. On the right and left it is to the right and the left. Okay. Whenever it points in the same direction as small n, n cross n is equal to 0, okay, because if the two are directed in the same direction, the cross product of two parallel vectors has to be equal to 0. So, the integral over the top and bottom surfaces is identically equal to 0. What one is left with is the integral over the sides. Okay. So, this is also equal to one by delta V integral d sigma over the sides alone of A dot n cross n. Okay. And what is the integral over the sides? Okay. Over the sides, the outward unit normal n is pointing in this direction, whereas the outward unit normal capital N is actually pointing in these directions. So, if I take n cross n, I get a vector which is perpendicular both to small n as well as capital N. That means that integral has to go along this path. Okay, that means the integral has to go along the perimeter of the intersection between this volume and the surface. Okay, it has to go along the perimeter of the intersection between this volume and the surface. Okay. So, that vector along the perimeter, I will call it as, let me use a different symbol here. So, this is my intersection of this differential volume on the surface. This was this was capital N. Okay. Small n is coming out of the board at me. Okay. Small n is coming out of the board at me. Capital N is in this direction. So, if I take n cross n and I use the right handed coordinate system, I get a vector that is pointing in this direction over here. Okay. On this direction you will get a vector that is pointing in this direction because n is this way. Over here it will be coming in this direction because capital N is this way, and at the bottom n is directed downward. So, I will get a vector n cross n which is in this direction. Okay. So, this I will call the tangent vector to this contour, the intersection between the volume and the surface. Okay. So, this thing becomes 1 over delta V integral over the sides of d sigma of A dotted with this tangent vector, the tangent vector along the four sides. Okay. Directed in the direction of the cross product between capital N and small n. Okay. In this particular case, since we are using a right handed coordinate system, we use the right hand rule. Okay. So, I have integral only over the sides. Okay. The top and bottom integrals are 0. I have integral only over the sides. Okay. The surface area of the sides is equal to this contour length times the height h. Okay. Is equal to the contour length times the height h. The volume is equal to this patch of surface, this area of this patch of surface times the height h. The volume of this box is equal to this the volume of this patch of surface times height h. The surface area of this surface is equal to this path length times the height. So, I get 1 over delta s times h integral over the sides of h dx, where dx is small displacement along this path and h is the height perpendicular, times a dot t. Okay. And the two h's will cancel out and I will get 1 over delta s integral. Okay. Now, since the h's are cancelled out, the integral is only over dx. So, it is integral over the length, okay. dx dx a dot t. Okay. And this I can also write it as 1 over delta s integral dx vector dotted with a. Okay. I can also write this as 1 over delta s times dx vector dotted with a, where dx vector is equal to the tangent vector times the displacement. Okay. So, let us put that all together here. Okay. So, I have this path going around this surface. This is the surface delta s. Okay. This is the tangent vector at each point. Okay. And differential displacement is dx. Okay. So, this vector displacement is dx times t, which is just dx vector. Okay. So, therefore, from my previous lecture, from my previous page, I have n dot curl A is equal to integral, okay, of dx vector dotted with A 1 over delta s integral dx vector dot A. For this small little patch delta s, okay, this is true only for this small little patch delta s. Note that this is an integral over the entire path. Okay. So, this is a cyclical integral, okay, which goes all the way from the beginning to the end. Okay. So, it is an integral over the entire path. So, this is for each little patch on that surface. Okay. If you recall, we had this entire surface here and we had taken only a little patch on that surface. For that little patch, we showed that integral of d delta n dot curl A is equal to 1 over delta s times integral dx dot A. Okay. Alternatively, delta s n dot curl A is equal to integral dx dotted with A. But my original integral theorem was for the entire surface. The original theorem was for the entire surface. So, how do we get it from this microscopic relation? Once again, we use the same little bit of logic that we used for calculating the divergence. Okay. So, I have this surface here with this perimeter. Okay. Surface has an outward unit normal n, okay, and this perimeter C is the perimeter of the surface. Okay, this perimeter C is the perimeter of the surface. This relation that I have is for each little patch on that surface. Okay. So, what I can do is take this entire surface and cut it into small little patches. Okay, cut it into small little patches. Okay, cut it into small little patches. For each little patch, this thing works. Okay. So, if I take two adjacent patches here, okay, let us say I take two adjacent patches, I and I plus 1. Okay, so, I have two adjacent patches, delta s I and delta s I plus 1. Okay. I know that the total integral ds n dot curl A is equal to summation over all the patches I of delta s n dot curl A, okay, over all these patches. For this patch S I, right, this integral of delta S n dot curl A over this patch S I is equal to, okay, is equal to integral dx dot A over the contour C I, where C I is this particular contour, integral over this contour. Delta S I plus 1 of n dot curl A is equal to integral over the patch C I plus 1 of dx dot A. Okay. So, for this patch you go in this direction. Okay. There is one line that is common between these two, a piece of the contour that is common between these two, and that is this, the right side face for S I, the left side face for S I plus 1. They are identical. I just separated these out to show that they are two separate patches, but they have a common boundary between them. Okay. If I take this integral delta x dx dot A, okay, A is the same on that line, okay, it is a single valued function. For the left side, I am going in an anti-clockwise direction around this path. So, I am going upward, okay. My x vector is upward for the left side, x vector is downward for the right side, because once again I am going in the according to the right hand rule in the anti-clockwise direction. So, the values of this contour integral on this one and this one are equal in magnitude and opposite in sign, and therefore, they will exactly cancel out. Okay. That is true for all pieces of the contour that are in between any two adjacent surface patches. Okay. All pieces of the contour that are in between two adjacent patches, the direction of the tangent vector will be opposite if you use the correct right hand coordinate rule, whereas the value of the vector itself is the same. So, these two will cancel out on all adjacent patches, okay. And the only thing that you will be left with is the integral over pieces of the contour that are not between two adjacent patches. Okay. What you will be left with is pieces of the contour that are not between two adjacent patches, and that is the only piece of the contour that is not between two adjacent patches is this perimeter of this surface. Okay. The only piece of contour that is not between two adjacent patches is the perimeter of this surface. Okay. Therefore, this proves that integral over the surface of n dot curl A is equal to integral over the perimeter of dx dot A. Okay. Exact same bit of logic that we had used in the divergence. In that case, we looked at the surface integral between adjacent surfaces. Unit normals were in opposite directions, and therefore, they cancelled out for all parts of the surface which were between adjacent volumes. Same thing here for all parts of the contour which are between two adjacent surface patches. Okay. Okay, so, this is the integral theorem for curl. Integral ds n dot curl A is equal to integral dx vector of over the contour. Okay. So, this relates a surface integral to a line integral, and like the other theorems, it also has consequences. The first consequence is that this integral over the surface of n dot curl A, I have reduced it to an integral over the line of dx dot A. That means that this surface integral does not depend upon the value of this vector on the surface, it only depends upon the value of this vector on the perimeter itself. Okay. It does not depend upon the value of the vector at all points on the surface, It only depends upon the value of the vector on the perimeter of the surface. Okay, that is one important consequence. Second important consequence, I could have many surfaces which have the same perimeter. Okay. Just as in the case of the integral for the gradient, I told you that I could have many different paths between 2 points. In this particular case, I could have many different surfaces which have exactly the same perimeter. One could be this surface, I could have some other surface, okay, which is not the same as this one, which has exactly the same perimeter. And the implication of this integral theorem is that n dot curl A over all of these surfaces has to be exactly the same. Okay. So, for an open surface with a perimeter, any surface which has the same perimeter has to have exactly the same value of n dot curl A, provided n is the outward unit normal and the curl is taken with the right hand rule. Second consequence, if I had a closed surface has no perimeter. Okay, the perimeter of closed surface is basically a point. That means for a closed surface, integral over the surface of n dot curl A has to be equal to 0. For any closed surface, integral over the surface of ds n dot curl A has to be exactly equal to 0. Okay. Physically, what does n dot curl A mean? It is precisely what I had done earlier. This integral over the ds of n dot curl A is basically equal to the value of this function dotted with the tangent along the perimeter. Okay. So, in this case, if A were, for example, a velocity field, okay, this integral ds n dot curl of the velocity is equal to integral dx dot the velocity. Okay. Displacement dotted with the velocity integrate over the entire perimeter. Okay. So, if I have a perimeter that looks like this, I have the velocity vector at various points pointing in various directions. I take a small patch of surface, integrate the tangent along the surface times the velocity, I go all the way around. It will tell me whether there is a circulation along this path or not, okay, whether the velocity is circulating around this path or not. Okay. So, that is the physical implication of the curl. Okay. So, these are the three fundamental elements of differential vector calculus. Each of these has an identity independent of the underlying coordinate system. It has an equivalent integral relationship and it has its own physical interpretation. Okay. So, when we do vector calculus, we will work in terms of these, we will not work in terms of derivatives in a specific coordinate system. So, in the next lecture, I will briefly discuss, in this case we had derived it for a Cartesian coordinate system which was relatively simple. Okay. What happens if you do not have a Cartesian coordinate system? We often work in terms of spherical or cylindrical, as we saw in Fundamentals of Transport Processes 1. In that case, how do you derive vectors, the gradient, divergence and curl in those coordinate systems? So, I will briefly see that in the next lecture, because in those coordinate systems, as I said, the unit vectors themselves are functions of position. Okay. And we will look at how to define gradient, divergence, curl in those coordinate systems before we proceed to look at fluid mechanics proper. So, we will briefly deal with these quantities in a non-Cartesian coordinate system, but still orthogonal. That is, the coordinates are not directed, the unit vectors do depend upon position, but at each point in space all three unit vectors are perpendicular to each other. So, it is an orthogonal coordinate system. We will see that briefly in the next lecture before proceeding to fluid mechanics. So, kindly revise what all was done in this class, because this forms the basis of what we will be using later on.